Bismillahirrahmanirrahim. Assalamu alaikum. Today we will discuss eigenvalues and eigenvectors of a tensor. Suppose we have a tensor T and we will say that this vector A is an eigenvector of this tensor T if we have this equation. What does this equation tell us? That the transformed vector, which is TA, will be equal to lambda times A. That T is transforming A into a vector which is parallel to vector A itself. Then we will say that this vector A is the eigenvector of tensor T and lambda is the corresponding eigenvalue of tensor T. This is the same definition which you have already studied in your previous classes, in which you have used Ax equal to lambda x, where lambda is the eigenvalue and x is the eigenvector corresponding with eigenvalue lambda, and A is any n by n matrix. Here we are talking about only second order tensor. Second order tensor means that we have a 3 by 3 matrix. No, you know that tensor T is linear. So by using the linearity property, we can have some other results. We can write T is applying on alpha A, and we can write this alpha times T because what T is linear, so we can alpha is scalar and T is linear, so we can take the alpha outside and we can write alpha times TA, and we know that A is eigenvector of T, so we can write instead of TA lambda A, and also we can write here lambda into alpha A. So we can say from equation 2 that if A is an eigenvector of T, is eigenvector of T with eigenvalue lambda, then alpha A is eigenvector of T with same eigenvalue lambda. With same eigenvalue lambda. What is alpha? Alpha is scalar. 2a, 3a, minus 4a, minus 6a, whatever scalar number. So this result is coming from the linearity of this tensor T. Linearity of this tensor T. That if you have an eigenvector A with eigenvalue lambda, then any vector parallel to A will also be an eigenvector of T with the same eigenvalue lambda. A tensor T may have infinitely many eigenvectors. That a particular tensor can have infinitely eigenvectors. Suppose that you have identity, and we know that identity is a tensor. We can write IA equals to A, because this is identity transformation, though, so it will transform this A into A. So if you will observe this equation, then you can say that A is eigenvector with eigenvalue 1, and whatever the A is, this equation will be satisfied. So any vector A is an eigenvector of this identity transformation with an eigenvalue 1. So it means that this identity transformation, which is basically a tensor, has infinitely many eigenvectors and with eigenvalue 1. For all eigenvectors, eigenvalue will be 1. So if we have this, that you have identity transformation and you have beta times identity, that you have any scalar multiple of your identity transformation, you can write beta times A equals to beta IA, and you know that this IA equals to A. Beta A is equal to beta IA equal to beta A. So here lambda is beta, so it means that if A is eigenvector for identity transformation I with eigenvalue 1, then A will also be eigenvector of the tensor beta I with eigenvalue beta. Here A is eigenvector of identity transformation with eigenvalue 1. Here A is eigenvalue of the transformation beta I with eigenvalue beta. We have one more result for this eigenvector, that if you have a rotation tensor T, then only those vectors which are parallel to the axis of rotation will be eigenvector of that tensor, because only those vectors will remain parallel to themselves. That is why they are the eigenvector of that tensor. Because if you have rotation axis along x3 axis, then you know that your rotation matrix, if it is R, will not change, that E3 which is parallel to x3, R3 is equal to R, E3 will be equal to E3. So E3 is the eigenvector of R with eigenvalue 1. Now we will further see suppose that you have an eigenvector and its length is 1. Suppose it is small n, that we have n is a unit eigenvector of tensor T. Then we can write Tn equals to lambda times n. This is by definition, that we are saying that n is the unit eigenvector of this tensor T. So what we can write, we can write Tn equals to lambda times n, and this can be written as lambda times in. So we can take this on left hand side, and we have this equation, and after this we have this equation number 3. Now we will write this equation number 3 in components form as this, where n is alpha I ei, alpha 1 e1 plus alpha 2 e2 plus alpha 3 e3. So components form of equation 3 will be this IAG, and IAG we are going to write delta delta ij. So if you will vary the indices j and index I and open the summation on j, then you have equation number 4. Solution of this equation number 4 will give you the eigenvector, and we can see that alpha 1 alpha 2, this is basically homogeneous system in alpha 1 alpha 2 and alpha 3, and we know that homogeneous system always have a trivial solution. Alpha 1 alpha 2 equals to alpha 3 equals to 0. This solution must satisfy equation number. So if you will use this type of solution, then you will have 0 eigenvector. But when we start our eigenvector, where we will say that we must have non-zero eigenvector. As your previous classes, you are always used to say that ax equal to lambda x, where x is not equal to 0. No, to find the eigenvalues, we can write the characteristic equation, which is a t minus lambda I equals to 0. Now solution of this equation will give you the eigenvalues. Eigenvalues of t. Now you can see that this equation will be a cubic equation in lambda, so there will be 3 eigenvalues. And from equation number 4 you have eigenvectors for each eigenvalue, and also you will use this condition. With this condition, alpha 1 square plus alpha 2 square plus alpha 3 square is equal to 1, and equation number 4 you will have unit eigenvector for eigenvalue lambda. This is due to the unit length of your eigenvector small n. Now let us see an example. Suppose that you have a tensor t 2 0 0 0 2 0 and 0 0 2. We have to find eigenvalues and eigenvectors of this tensor t. If you look at this matrix, then you can write t is equal to 2 times identity. Identity is 1 0 0 0 1 0 0 0 1. This is the same as you have beta I here, beta I, where beta is 2. So you can write TA equals to, instead of t we have 2I, so IA is always a, so we have v2a, so ta equals to 2a. So, and any vector a is eigenvector of this tensor t with eigenvalue 2. This is same where we said that a is eigenvector of tensor beta I with eigenvalue beta. Here tensor t is 2 times I, beta I, where beta is 2. You can also have the eigenvalues and eigenvectors from the following characteristic equations. This is coming from question number 5. T11 is 2, T22 is 2, T33 is 2, and all others are 0. So we can write 2 minus lambda, 2 minus lambda, 2 minus lambda, and you will have eigenvalues 2, 2, 2, 3 eigenvalues, and they are repeating 2, 2 and 2. So for eigenvectors we will use equation number 4. You will use lambda is equal to 2 in your equation number 4. 2 minus 2, 2 minus 2, 2 minus 2, all others are 0. You will have 2 minus 2 into alpha 1 is equal to 0, 2 minus 2 into alpha 2 is equal to 0, 2 minus 2 into alpha 3 equals to 0. This system will be satisfied for arbitrary values of alpha 1, alpha 2 and alpha 3. Why? Because 0 times alpha 1 equals to 0, 0 times alpha 2 equals to 0, 0 times alpha 3 equals to 0. So any vector will be eigenvector of this tensor T with eigenvalue 2. And you can choose 3 independent eigenvectors. In particular, you can have basis EI as set of linearly independent eigenvectors. That they will be linearly independent and also their length will be 1. E1, E2, E0, 1, 0, 0, 0, 1, 0, 0, 0, 1. That alpha 1 is 1, alpha 2, alpha 3 0, 1 eigenvector, alpha 2 is 1, alpha 1, alpha 3 0, second eigenvector, alpha 3 is 1, alpha 1 and alpha 2 is 0, third eigenvector E3, E1, E2 and E3, basis as set of linearly independent eigenvectors. Now we have another example. In this example we are saying that if you have a tensor T in which T21 T31 equals to 0, and if then what you have to show? You have to show that plus minus E1 and minus E1 is an eigenvector of tensor T with eigenvalue T11. That if you have a tensor T and if these two components are equal to 0, then this will be an eigenvector of tensor T for eigenvalue T11. This you have to show. So it means that what we have to show? We have to show this and this, that Te1 will be equal to T11 E1, that T is transforming this E1 into T11 E1 parallel to E1, any vector parallel to E1 which is T11 times E1. This we have to show, because we know that we have to show T11 eigenvalue for tensor T corresponding eigenvector E1. Basically we have to show T11 E1 is eigenvector with eigenvalue T11, and again we have to show minus time E1 will be an eigenvector of T with the same eigenvalue T11. So we have to show this type of equation. We know that Te1 equals to T11 E1 plus T21 E2 plus T31 E3. This is from your lecture number 2, I think, or lecture number 1, that in which we have written components of tensor T. T1 equals to this, and we are given that T21 T31 they are 0, so it means that T11 E1 plus 0 times E2 plus 0 times E3, so plus 0 and 0, and we have Te1 equals to T11 E1. Now this equation is telling us that E1 is eigenvector of tensor T with eigenvalue T11 when you have T21 and T31 equals to 0. Now you have to show that minus E1 is the eigenvector of T with the same eigenvalue T11. So you know that T is linear, so you can write T of minus E1 equals to minus time Te1, and we know that E1 is eigenvector of T, so we can write instead of this thing minus T11 E1. So we can write T11 minus E1. This equation is telling that minus E1 is the eigenvector of tensor T with eigenvalue T11. Similarly, if you have T23 and T13 equals to 0, then plus minus E3 are eigenvectors corresponding to eigenvalue T33. And if you have T12 T32 equals to 0, then plus minus E2 are eigenvectors corresponding to eigenvalue T22, and you have to do this by yourself. This is a question from exercise. Start from 2B32 to B34. Now please go through this lecture, listen this carefully, and if you have any question, any query, then we will discuss the questions in tomorrow lecture, inshallah. And please go through this, and this will take only your 25 minutes hardly. Thank you so much.